All right. Um, Turning power, right. So is drifting, it looks like later on this is used a lot and figured out if it's true or false. So I'll look at it later. But if we're drifting, then drifting turning power, then we grab this, which appears to be a float. Otherwise, we take our turn input and multiply it by our steering factor coming from our stats. All right. So our turning power is impacted if we're in a drift or not. Um, so turn angle. So quaternion, we're dealing with a rotation. And angle axis. So creates a rotation which rotates angle degrees around an axis. Okay. So basically, we're going to take our turning power and rotate around transform up. So what that means is we're going to take a vector. Oh, no, I'm sorry. It's a float. Take a float as the angle. Okay, so an angle is like, 15, 30, 60, 90, all the way up to 360. And then rotate it about transform up. That means our local up. So whatever. So if I take the cart and the green is pointing up, right? So whichever, no matter how we're rotating, green's always up. But if we are like going up a ramp or something, notice how our green up is a little different because we're not flat anymore. We're scaling up. So what it wants to do is it wants to create a rotation around the green. So think about rotating around the green like this. So if you imagine, I know rotations are hard to think about, but if our up is this, and I know this is rather light, but since this is the axis, we're talking about rotating around it, which means that the flat around it, you can see the green line right there. That's why the rotation axis for green up is around it. We're not, think of like it's like a cross section of it. Like think about the up axis is like the normal. It's like the perpendicular angle, and you're rotating around it. So that's why the green circle is perpendicular to it. So if we were saying, instead we're saying, hey, rotate around your local z, which would be pointing down the road because we're looking down the road. Notice how the blue circle is going this way. We'd be like rotating like this. And notice how the red, if we're saying, hey, rotate around our local right, our x, it's this one here. So rotations can be tricky. So notice with blue, if we're saying, hey, rotate about the local z, we would be kind of rotating perpendicular to z. And here we're rotating on the up, which means we're rotating perpendicular to y. And same with red. Notice how we're flipping around that axis. I can say that 3D rotations are one of the more difficult things to wrap your head around. But this is saying, like, how much should we be turning from like 0 to 360? It's an angle in degrees. We're rotating about the up. So it's like we're turning left to right. This is how we get our turn angle, because we're turning perpendicular to up. Okay, so vector 3 forward. Take that turn angle and multiply it by our forward direction. So this is going to give me a quaternion, which is a structure dealing with rotation. And so we're going to take a quaternion multiplied by a vector 3, which I don't really do because that's mixing too, but it looks like we get a vector 3 out of it when you multiply a quaternion. It's a quaternion operator, and you multiply a quaternion by a vector 3. You multiply a rotation by a point, and you get a vector 3. Sure. So we get our forward vector 3. So I'm guessing this is our forward after our turn. So our transform.forward is like where we're pointing right now, right? So we're pointing down the road. And after the turn, let's say I'm holding on to the A key pretty strong for a lot of time or whatever, and we get this turn axis, like it's saying, okay, we're going to be doing something like this. And this is the quaternion, this is my local forward, and it's saying like, hey, this is my new forward. So the next frame or whatever, when we figure out our current velocity times this turning that's currently happening, it's kind of like predicting like, okay, our forward's going to be over here afterward. So I'm assuming that's what's happening. And so that's what this forward is here. And so then we take our new forward after our turning, multiplied by our acceleration input and our final acceleration. So what are we putting in with our input, and what was calculated here with like based on are we going forward or backward or braking or whatever. And now it's multiplying by this quaternion operator, the ternary operator. So are we in the middle of having a collision or not? Are we collided? Or is ground percent greater than 0? Okay. So are we in a collision, or are at least one of our wheels on the road? Then we get 1. Oh, I'm sorry. This is not a collision. This is like, is our collider touching something? Are we touching the ground with that main one of the colliders? So we have that this bouncing, this big capsule here, and we have these colliders down here. And remember, they're checking like, are we touching the ground, or is one of our wheels been recorded as touching the ground? Then that's great. Then we can just multiply this whole thing by 1, meaning don't change it. Otherwise, something's wrong here. We're not like touching the ground for some reason. Don't apply an acceleration. So we get a 0 movement, or we do get some movement. And then it was current speed over our max speed for whatever reason, then this bool is true. So if we're over speed and we're not braking, then we've already hit our max speed. Just kill this movement because we don't want to go past our current velocity. Like, we're maxed out on velocity at the moment. And then new velocity. Take our rigid body velocity and then add this movement that we've been calculating, which let's just say it's not 0. Let's say everything is fine, right? We have this forward, this accelerating input, this final acceleration. That's our movement, our vector 3. And then what we have to do is remember that when we're in update or fixed update, we have to multiply by this time dot delta time or time dot fixed delta time. That's the amount of time that's passed since the last frame, whether it's fixed update or update. So since it's variable, we don't know what it is. Well, we don't know what it is for update. We kind of know what it is for fixed update because it's fixed, but you're supposed to just use this anyway. You're not like go look up what the number is. This will have that number. And so like just to say it was like 0.1, like 1/10 of a second. Well, then this movement that was calculated is like in seconds. Like whenever we talk about movement, there's some time to it. So when you talk about velocity, it has to be like meters per second or miles per hour. Whatever it comes out to be when you're working in the update or the fixed update, you got to multiply it by this because we're not in a second or an hour. We're in a little fraction of a second. So when you multiply it by that little fraction, this movement gets chopped down. Let's just say this movement was meters per second. Well, when you multiply it by like 0.1, we then convert that down to 1/10 of a second so that we get accurate movement. But once that happens, all we do is add that to our current velocity. And then that's our new velocity. And then it looks like, hey, whatever the y was that we just calculated, just go back to our original y from our rigid body for whatever reason. So it looks like they're doing a lot. I just wanted to make a quick note. They're doing a lot of their like turning manually. Like you could let the kind of rigid body take into account, like if you're accelerating forward, pressing A, but you're also pressing like pressing W, but you're also pressing A and D to move to turn a little bit to left and right. You know, you could add some velocity into that left and right and see how it works. But usually, the better that you understand this physics and you can like manually write out, usually the better the results you're going to get. So clamp max speed if we're on the ground. So if ground percent's greater than 0 and we were over max speed, then clamp our magnitude of our vector 3 to whatever we were, the new velocity to whatever our max speed is. So when we're clamping the magnitude, the size, we're not adjusting the direction of this vector. We're just changing the size of it, the scale of it, the magnitude of it, if it's gone past our max speed. So coasting is when we aren't touching accelerate. Okay, so take accelerate input, give me the absolute value of it, make it positive if it was negative. And if this is less than our null input, which looks to be 0.01, so it's a really small number, and our ground percent, at least one of our wheels are on the ground, then we're coasting is when we aren't touching accelerate. Okay, so if somehow we have an accelerate input, okay, if we're not, okay, no matter what, if positive or negative, it's less than a small number. So if we're not, user's not pressing any forward or backward, and the wheels are on the ground, then we want to coast. So vector3.move forward. Calculate a position between the points specified by current and target. Okay, so this means this is vector3 is current. This is where I currently am, right? And vector3.target is move me towards that location, but you might not go the whole distance to that. And move no farther than the distance specified than the third value, max distance. So new velocity. So it's like take whatever our new velocity is. This is if we're coasting, but we have some like new velocity was calculated. And then the second one is new vector 3, 0. So take whatever our velocity was in the y currently, but get nothing x, nothing in z. Okay. And the third thing is how far should we move in that distance? Take the like little time unit that's happened, fixed delta time, and multiply it by whatever our coasting drag is. How quickly the cart will reach a full stop when no inputs are made. Okay. So a drag when you're coasting and you're so it's like slowing you down a little bit. If you're actually moving, if you have a velocity but you're not like accelerating, you're not pressing any of the input. They want to like drag. They want to like kind of slow you down slowly, but not like instantly stop, and not just have you just like keep moving along at a constant like velocity where it feels like you should be slowing down your car on the road and you're not hitting the gas pedal. Normally, when you have a rigid body and you add a physics material to it, like all this type of drag and friction, like you can set the numbers, and this is all done for you. I'm not really sure why they're writing all the code for it, but when you write your own code, you get to customize it. Basically, you don't have to just follow the standard conventions given to you. But in any case, this gives us a slightly new velocity for our coasting. And then after all that, then take rigid body velocity, pass in this new velocity vector into it, and this will be calculated in physics. Like there's a rigid body, here's the velocity, and then it'll do its physics simulation for that frame and update all the parameters. So drift. If we have at least a tire on the ground, and if we're in air, then set that to false and then instantiate a jump VFX. Okay. So if we have at least one tire on the ground and something did a check that said, oh, we're in the air now, whatever that calculation might be, then at that moment, that frame that this is true, that we were determined to be in air, maybe like 3 of the tires like left the ground or something, and there's just like 1 remaining or whatever the check is, then let's just say we're not in. Let's set this to false because we just instantiate. We don't want to do this again next frame. So manual angular velocity coefficient. All right, angular velocity steering. So angular is like your velocity, your turning velocity basically. In steering and smooth speed, these numbers are set. Sure. Turning is reversed if we're going in reverse and pressing reverse. All right. So if we're going in reverse, if this is false, and our acceleration, we're hitting the reverse key, then angular velocity steering, we multiply by -1. This gets flipped into negative. And rigid body dot angular velocity. So this is how quickly the rigid body is turning, not a linear acceleration going forward, but how much velocity is in the swinging, the turning of it at the moment, angular velocity. And that's measured in radians. Just be careful that you can measure an angle in degrees, like 360, or radians, which are in pi. It's a different way to measure angles, and there's like a conversion between the two, so you just have to be careful, like you just have to check like what you're in. So radians. So here's a good comparison here. So notice we have 0, 90, 180, 270, 360. But there's another actual measurement is in pi. So 2 pi is like a full rotation or no rotation. And you can see these like pi over 6, pi over 3, pi over 2. And so pi is that magic number, 3.14. So anyway, you just need to know. Sometimes it's easier, and the math is easier to use radians. A radian here, 1 radian, like 1 arc length. So how far along the circumference for the amount of radius of the circle. So 1 radian, you can see it's only about like 6 or so like radians. It's like they're kind of big chunks. Like 1 degree is just like a little slice of a circle. 1 radian is actually kind of a big chunk of a circle. And actually here's the conversion right here. It's about 57 degrees. It has to be like, if this is the radius of the circle, how far along the circumference of the circle can we go for 1 radian, 1 rad? So anyway, just something to be aware of. So move the y velocity towards our target. So now we're doing another like move towards. Take where we currently are in the y rotation. Because if you remember, the y rotation like turns us left and right. Like that's the one that we're interested in. Turning power times angular velocity steering, like that's where we're moving towards. This is going to generate a vector 3. Then how far are we going to move that way is the fixed delta time times our angular velocity smooth speed, which, what was it, like 20 or something? 20. And this is going to be a little fraction of a time, like 0.1 or 0.2 or something. So if it is 0.1 times 20, it's like 2. We're going to move like 2 units. The delta, I have to look that up. I don't know if it's like move 2% toward current to target or whatever. But in either case, we have we set the y to that, and then we throw that into the angular velocity of our rigid body. And then rotate the rigid body velocity as well to generate immediate velocity redirection. Okay, velocity steering, manual velocity steering coefficient. If the cart lands with a forward, not in a velocity direction, we start the drift. Okay, so if we have some type of wheels on the ground and our previous wheels on the ground was super small, meaning we just looks like if we just landed, then we could start a drift. All right, I'm just checking how much is left here because I'm running out of time. Almost. I don't know if I'm going to get through all this. Drift management. I think I might save. It looks like we're entering. I think I'm going to stop here because here we're just starting to go into like a whole part on the. This is all related. It's just drifting. It's a new part. So drift, 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 drift. And then rotator velocity. Then do a ray cast. And airborne, half on ground. All right, I think I'm gonna stop here. We went halfway through like this whole move function, and we'll wrap this up on Tuesday. So let me, I'm gonna stop the video.